Okay, so Świętorzecka is Sand River. So, at first I wanted to say that I am very honored that I can take part in your meeting. We came together with my doctorate student Marcin Łyczak from Warsaw. I am a professor in Warsaw University of Cardinal Stefan Wyszyński. And we prepared something about, which is, let's say, addressed to bridge between logic and philosophy. This is our, let's say, area of interests. I will start maybe with some anecdota. There was a situation when Platonics met Aristotelians, and they were quarreling because Platonics wanted to know how many teeth should horse have by definition. And Aristotelian said, let's go to the stable and count. And in this respect, maybe only in this respect, I am Aristotelian. So I prefer simply to do philosophical logic or philosophy with the use of logic than to speak about this. We decided to focus on the notion of modality, and as philosophers we were looking for the biggest authority. And I think it is not questioned that Leibniz is a great philosophical and scientific authority. And he was very interested in the notion of modality in many different senses. We were focused on two types of modalities, which we found in his works. In general, he describes three types: metaphysical, hypothetical, and moral. We left aside moral, because we are moral. And so we were concentrated on a metaphysical, or in other terms, absolute modality, and hypothetical modality. For this reason, we used already existed logic, which was associated with Leibniz. The logic is called LC box. And this is a logic, very simple one, sentential modal logic, where we formalized the notion of change as prior to time. This is obviously also characteristic standpoint of Leibniz. Leibniz was convinced that ontologically prior to time is change. And thanks to change, we discover and we have a feeling of flowing time. And this idea was my, let's say, idea for some years, how to modelize these notions, time and change, to get some logic in which we can simulate this situation that change is prior to time. So in effect, we got the following logic. Logic is propositional logic. It is based on classical logic. C, we can read, it changes that. And so we can add to sentential, to classical propositional logic, these axioms, and take some rules, and we have some logic in which we can define the notion of being next. It comes out that this logic is complete in linear structure, temporal linear structures, and so nothing really very, let's say, big, but philosophically quite interesting that you don't need to assume time. You can start with change, and then you get some temporal notions. By time, I added to my logic, which really was only this part, I added also the notion of necessity, symbolized by box. But this necessity was understood in a sense to be unchangeable. I mean, not to be changed all the time. This UC is here defined. You see it's a operator which tells you that from one state to the next state nothing changes. And so if something is necessary, then it does not change at all in any time point. And in effect, we got such a nice logic, which we made axiomatization together with my supervisor, Professor Johannes Czermak. And now we took this logic with us, and we started to think about modalities. Modalities in sense of hypothetical and absolute necessity. How to add it? Of course, one thing is to read Leibniz by himself, and the other thing is to read interpretations. In this case, many times interpretations are more fruitful than my lecture of Leibniz. I used for my next steps many known interpretations of texts of Leibniz. So Russell's known book about Leibniz, then I considered some investigations presented by Benson Mates, then by Adams, then by Jaakko Hintikka. And this last author gave me some very important, let's say, intuitions which I wanted to keep in our new formalization. What we know about necessity in sense of metaphysical necessity and hypothetical necessity. Russell claims that both notions are not explicitly defined by Leibniz, only they are simply used. What is told by Leibniz to us is that metaphysical necessity applies to logical laws. Also, metaphysically necessary are geometrical and mathematical laws. What is written but not explicitly, it's interesting, by Leibniz, is that metaphysical modality happens in all possible words. From syntactical point of view, it is said that negation of the sentence of proposition which is necessary in absolute sense is it implies a contradiction. Then, concerning hypothetical necessity, also it is not defined, although there are many philosophers which claim that the reason that Leibniz introduced hypothetical necessity is that simply he used this so-called Slake's rule, which is the following. When you have necessary A implies B, and A, then you can say box B. Of course, this rule is not valid in the sense that implication doesn't work, but it is applicable to logical laws. So in this sense, it is nothing wrong. And because Leibniz wanted to have such a similar way of reasoning, say, okay, when from A you can by necessity implies B, and A is only contingent, then B maybe is not absolutely necessary, but hypothetically necessary. So it is necessary in, let's say, depending on some contingent premise. What is more known about hypothetical necessity? They are conditioned by existence of individuals. All existential propositions about individuals are contingent, but there is only one exception. The thesis about existence of God. This is necessary. Concerning all other existential propositions, they are contingent. And if something is necessary, independence of existence of anything, of course abstracting from God, then it is only hypothetically necessary. What's more, everything what I what I had in mind, I said. And now, just a second. Oh. What our problem was to confront Leibniz's notion of necessity with constancy. Because we had in our logic this box which was planned to have that something is not changeable or does not change at all. So how to make a calculus in frame of which these two modalities would be different? I mean necessity in Leibnizian sense and constancy in sense of our box. Concerning this problem of, let's say, different way of thinking about constancy and necessity, we found a very interesting book of Lovejoy. He was historian of ideas, and he found, let's say, a principle which he was very, how to say, proud of it, and he went through history of philosophy starting from Plato, and he called this principle of plenitude. He discovered it in many places, in many texts of philosophers. He claimed that Plato was the first who explicitly was convinced that this principle was valid. And then also Hobbes, Spinoza, Descartes, and also in some contexts Leibniz. And in this problem also there were some investigations made by Jarkko Hintikka done, and Jarkko Hintikka was in opposition to Lovejoy. Namely, he said, okay, Plato, yes, but Aristotle also, time to time, was, let's say, inclined to assume this principle, especially when you take the net of Aristotelian notions, constancy, contingency, and necessity. And so this is, discussion between Lovejoy and Hintikka, and we applicated this problem to notions of Leibniz, to constancy and to necessity. We wanted to keep this distinction. We wanted to avoid this principle of plenitude concerning Leibniz. We were concentrated now on hypothetical necessity because we claim that this absolute necessity, it is simply, let's say, equivalent to be a logical thesis. So this notion can be defined in meta language as to be valid or true in all structures which are considered. And so we took in our language only hypothetical necessity. But to simulate ideas of Leibniz, somebody cannot or shouldn't ignore net of Leibnizian notions. And this is, let's say, forest. There are many specific K concepts which are involved in describing also hypothetical necessity. Many of these notions are, let's say, known, but of course there are many discussions about, let's say, definitions or explanations or explications of these notions. What we wanted to keep was that Leibniz was considered, as a creator of monadology. So he claimed that in reality there are these so-called atoms, which are everlasting, which were created by God, and they are called monads. Monads, they have some activity, and thanks to this activity, they have some simple properties. These simple properties are, let's say, adhered to monads, and this create states. States are connected by causality relation, and because of it, they form some chains of time. And this was our first approach. Now, we wanted to incorporate in this small part of this whole forest the second part, which are connected with the notion of possible word as the combination or the set of general concepts which are applied to monads. So, after these lectures, after our analysis, we considered the following simple model, which was the beginning of our generalization and of our making some logic. Let's imagine that we have infinitely many monads and infinitely many properties. Both sets, let's take it as ordered. Then we will take time points, and possible modes of monads are temporal, let's say, triples. If you will take any monad and some simple property and some time, you can say that this monad possesses this property in this time point. So, because these sets are ordered, we will take indexes like that instead of this notation. Let's now imagine that we have some constant fixed function which takes to every such a triple values 1 or 0, which describes all attributions or non-attributions of some properties to monad. I mean, when our function C takes some monad M1 and takes some property Pj, or let's say P2, in some time, let's say 3, and it is 1, it means that this monad possesses in this time this property. Otherwise, our function gives 0. So we can think now about simulation of individual concepts which are, which inform us which property is possessed or not possessed by individual monad. We can take simply such sequences which are constant concerning monad and constant concerning time, and now we have information which properties are possessed or not possessed by this monad in this time m. So, for example, if we would take, let's say, 1, 0, sorry, I can't. 1, let's say 2, 3, 1, 4, 3, and so on, and this would be, let's say, 1 or 0, then we will get such sequence which will inform you that in this time and this monad has or not has simple properties. So we can now take such sequences, and we will get individual concept of a monad individual concept of property here, and it is a monad, and this is the state on which it possesses this property or does not. All n simultaneous individual concepts are composable. Composibility is, again, some, let's say, specific concept of Leibniz. We know that some individual concepts are composable and some are not. Complete individual concept, it is all simultaneous individual concept through time. And now set of all complete individual concepts. It is such a set, and this is, in a sense, Leibnizian actual word. Actual word, it is a set of all complete individual concepts which are defined because we have this characteristic function. Okay, so now we can think about our necessity. What we can very easily say, we can take language in which alpha I k will be read some monad I possess property k, and this such a sentence will be interpreted as such a pair in our structure before, and now we can think, what does it mean that such a sentence is on point n true in our actual word? This is this case. In the same way, we can define negation, conjunction, implication concerning changing. Change is expressed in such a way that some formula A is changing on n just when these two are different. I mean, on n is A and or n plus 1 is not A, or on n is not A and on n plus 1 is A. 2 minutes? 20. 20, okay, thank you. So this is our change operator defined in our proposal, and then here there is box, but as we see, this box is simply a constancy. I mean, box A is true on n just when in all time points later than n it is true. And of course, in such a structure, you can get such implication, which is a version of this principle of plenitude. And this we want to avoid. Namely, if on our structure, on K, for every n, all the time something does not change, then it means that it is necessary. What to do? Proposal of Hintika is the following. This situation occurs because you have only one word. If you would link the notion of necessity with jumping to another word, then you could have a look what is in this another word, and then, let's say, it would be completely different situation. And this is a line of arguing that, in contrast to Aristotle, Leibniz didn't have this plenitude, I mean principle of plenitude, because he assumed that there are many possible words. So let's make it in the following way. When we have our possible word, it is PS and C. This C is this characterization function. Let's take the second one. Different at least on one place, somewhere. If it would be, then we could introduce our next modal operator, which we would read, it is hypothetically necessary than A. And what does it mean that hypothetically necessary A is true in our word? It means that when you will look into the other one, there it will be always true. So we have in result 3 modalities. One, it is C. The second is box, which is generalization of C. I mean, but it is not necessity, only changeability. And now we have the next one. It is the third modal operator, this H. Of course, all this story is told about some concrete actual word and about some concrete monads, even if they are abstracts. But our question is it possible to form logic for that? And we say, yes. And this will be presented by Marcin.
Maybe it won't be necessary. Yes? Yes? Okay.
Following Professor Świętorzecka, let's imagine that this line symbolizes flow of time in our actual world by next subsequent time moments. In our interpretation, something is changing if and only if it is true and in next moment it is false, or if it is false and in next moment it is true. And this constancy, let's say from here, for any formula B, formula B is constant if and only if it is true always in the future, right? But it can be false, for example, some here. And now, this is only actual world. If we want to say that something is hypothetically necessary, we need to jump to another possible world. Let's say foo. And something is hypothetically necessary, let's say here, if and only if there exists possible world in which A is always true. But truthness of hypothetical necessity of A is not connected with truthness of A in this world. So it's independent from this world. So in fact, we assume that in our structure we have at least two worlds, one actual and one possible. And this is the axiomatization. This axiomatization is divided into two parts. First part, we could say basis, is logic LC box of Professor Świętorzecka, which describe, we could say, one actual world. To interpret this axiomatization, we need only one line. And we add to this, this logic LC box 6 axioms. First, describe connection between hypothetical necessity and conjunction. There is no easy way to deleting this hypothetical necessity, as we see. Second axiom expresses connection between implication and hypothetical necessity. It is similar to axiom K of modal logic, but this is not K because here we have so in general K is not hold here for this modality. Last axiom for H is axiom 5, a little bit stronger, and it expresses connection between necessity and this hypothetical, between hypothetical necessity and negation. Now we have 3 axioms for hypothetical necessity and this constancy. Here, in these axioms, you can put inside this hypothetical necessity constancy and delete. Here we have a connection between constancy, hypothetical necessity, and disjunction. And in last axioms, we have that if something is not hypothetical necessary, it cannot change. It means that if something is hypothetical necessity, it is always hypothetical necessarily. We have the following rules: extensionality, logical laws, we could say, are not changing. And if you have implications, which is theorem, then if A is hypothetically necessary, then also B is hypothetical necessarily. We have also rule for introducing constancy, and this is complete. We have proved it using some version of Henkin method. And constancy, it is probably not surprising, has properties of modal logic as 4.3. This hypothetical necessity fulfills axiom 4 of modal logic. Maybe it is probably a little bit more interesting that what is not hold here. First, axiom T is not hold if something is hypothetically necessarily. It doesn't mean that A is true here. But what is more interesting, even D is not hold here. Why? Because simply if something is hypothetically necessarily, I mean here, it is also possible that there is some U in which there is always not A, right? So we simply have models in which you have A, and hypothetically it is necessarily that no A. Axiom K does not hold, and this last one we could say that this is expressed, that this principle of plenitude does not hold here. And that's